get started. Welcome, everyone. I'm really happy to introduce Professor Charles Driscoll from Syracuse, we're really happy that he's been able to visit MIT. He's from the Department of Civil and Environmental Engineering and is a distinguished and university professor. We're also particularly glad that we invited him in April because March Madness apparently was a very intense time at Syracuse. But now, yesterday was Red Sox opening day, so we can have even more excitement. Charlie's work is really very varied and talks about a lot of issues that we think about here on campus. Thinking about the issue of power plant carbon standards and their impacts on air quality, ecosystems, and human health. So with that, I'm just going to turn it over to Charlie.
Turn on my mic here. Well, good afternoon. Well, thank you for inviting me. I really have had a great day today. I've enjoyed talking with a lot of interesting people and learned a lot. So, let's see. Oops. I'm gonna have to figure this out. All right, and this is in the middle of things. Huh. Sure. So I'm trying to reverse it because it's not on the first slide.
Oh no.
Oh, this doesn't look good.
Sorry, everyone. Let's try this.
Here, go ahead.
Sorry.
Yeah, we thought we were all organized.
We got everything all set. Let's see.
Okay, as Noel said, I'm going to talk a little bit about a project that we've it's a sort of a two-part project. We actually started working on this a few years ago. I'll try to tell you a little bit about the backdrop behind the project. So we're talking about, first about we'll give you a little bit of background information, and then talk to you a little bit, the first project, that's going to be the bulk of the talk, which is pretty well completed, and then we are starting in a sort of a second phase where we're looking at the Clean Power Plan. This is part of an initiative of a group that I'm involved with called the Science Policy Exchange. Our overall goals are to try to do scientific synthesis and translation and associated outreach. So there are three areas that we work in. One is dealing with energy, others water, and then sort of land management and the interface among those three areas. So this is one of the projects from the Science Policy Exchange. Okay, so you may ask the question, what are co-benefits? I know many of you know what co-benefits are, but co-benefits in the context of energy issues, energy management associated with carbon dioxide control. We're interested in mitigating carbon dioxide emissions to address climate change. That's a prominent component of the U.S. Position recently in Paris to try to reduce our pledge to reduce carbon dioxide emissions. But people have a hard time relating to and understanding climate change, both the spatial scale and the temporal scale, but they're interested in co-pollutants, things that are associated with fossil fuel combustion that resonate with them. People are interested in local air quality. So co-pollutants would be things like sulfur dioxide, nitrogen oxide, mercury, particulate matter. And they influence regional and local air quality, and they have certainly health co-benefits and also ecosystem co-benefits. One of the things I'm interested in is to try to the health co-benefits are the big kahuna. I'm interested in also ecosystem co-benefits and the integration across those two. Part of this was try to turn the conversation on climate change towards things that people care about, local issues, and specifically local air quality. So the bottom line for this is that, and these are all no-brainers, if we shift towards more energy efficiency, cleaner burning fuels, we'll not only mitigate climate change, but we'll improve air quality, and there'll be health and ecosystem benefits. And there are good economic reasons for doing this. So the energy landscape is rapidly changing, and there's a lot of activities now that influence air quality and energy systems at the federal level. A lot of these deal with air pollution issues, such as the federal acid rain program, the mercury and air toxics, which is in limbo now, but certainly the cross-state air pollution, the federal regional haze rule, and some energy issues as well, and the Clean Power Plan, which we'll talk a little bit about today. But there's also very important state and regional activities as well, and a big driver is shifts in energy use towards natural gas. So as I said, there's lots going on at the state level. There are some states with carbon cap programs, the RGGI states, California. There are a number of states with renewable electricity standards, either standards or voluntary programs, as shown here, although it's not very clear on this slide, but there's a number of states here in blue with standards. And then states with energy efficiency standards. And if we look at across the distribution of energy use, coal is way down, natural gas and renewables are way up. So there's a lot going on, and it's changing very quickly. And there are air quality implications of this. This is a slide showing you trends in power sector emissions for carbon dioxide, sulfur dioxide, and nitrogen oxides. I'm going to use 2005 as a reference here because that's what the EPA used as a reference here for their analysis for the Clean Power Plan. We also have we started this study in 2013, so we also have that as a reference year, and then projections that we made for business as usual without a program like the Clean Power Plan and one similar to the Clean Power Plan shown here, driving down the emissions of carbon dioxide, but also these co-pollutants. Okay, so a little bit about the Clean Power Plan and the history behind this. There was actually a draft plan in 2014, and then the plan was finalized this past summer. The states, back when it was originally announced, have 1 year to indicate what their approach is to planning, and then the plans need to be developed by 2018, and then compliance beginning in 2022. So a reasonably aggressive plan with a 32% reductions in greenhouse gases by 2030 based from 2005 values. And as I mentioned, this is a central piece to the U.S. pledge in the Paris negotiations. But over the last few weeks, the Supreme Court got involved and there's a stay, so we're sort of in a timeout, so all these timelines are on hold. So the Clean Power Plan is being implemented through Section 111D of the Clean Air Act. It's an interesting approach. It's not a standard in the sense that we would normally consider a standard for traditional pollutants, but it's the best system of emission reductions. It's very much a state-driven plan. States have to have to put forward state implementation plans, and the states within this program have maximum opportunities for flexibility and trading and things like that. And there are many factors that come into play, including environmental outcomes in their decision-making process, and it's a public participation process. So as I mentioned, the plan is projected to cut carbon dioxide emissions by 32% from 2005 values for the year 2030. And there would be projected large reductions in sulfur dioxide and nitrogen oxide emissions. So that's the backdrop of information. A little bit about our our project that I'm going to talk most about, we actually started this back before the Clean Power Plan was announced. We knew nothing about it. We actually started this project with monies from foundations, and our goal was to try to evaluate coal's footprint. But then soon after we started this project, we heard about the Clean Power Plan. We wanted to do something to evaluate that, but we couldn't really get any specific information about the nature of the plan. So what we decided to do is we decided to look across different policy spaces, different policy outcomes that could be implemented. So we have a team of people who are indicated here who include health scientists, economists, people who are interested in atmospheric modeling, and we also have people who have done ecosystem effects. So it's a very diverse group. Many of these is the first time working together, so it's a new group putting together, and we've obtained funding from foundations to do this work, which in retrospect was smart. There are several aspects of this project that when I started, I had no idea how they would play out, but I have to say, of all the projects I've done, I was extremely lucky in this project because of decisions that were made, and one of them was the funding from foundations, but we'll talk a little bit about that later on. So the way we're implementing this project is there are a series of linked models. First, we do a variety of scenarios in a reference case that we developed, as I mentioned, across this policy space. And we put this information through a utility planning model called the IPM, the Integrated Planning Model. And so we have outputs in terms of energy distribution and emissions from this model for these scenarios. I'll talk about the scenarios in a second. Then we take that and we put this into an air quality model, CMAQ, which stands for Community Multi-Scale Air Quality Model. It's a well-vetted model. It's widely used by states, widely used by the federal government for air management decisions. One of the smart decisions that we made was we made spatially explicit calculations, which EPA didn't do, but we decided to do, and I think it helped us out a lot. Then we took the output for that and we put it into an epidemiological model, BenMap, to look at the health co-benefits associated with particulate matter and ozone from outputs. We also took that output and we used it in a variety of ecosystem assessments. So we looked at atmospheric deposition. We used an atmospheric deposition model to look at the effects of surface water acidification. I'm not going to talk about that, but that was a component of the work. We looked at visibility, impacts on visibility, and we also looked at ozone effects on crop production. Okay, a little bit about the scenarios because they really are critical to the overall story. So remember, this is 2013, so it's actually, in terms of what's going on in the energy sector, it's a long, long time ago. There's a lot that's gone on. We use the projected outlooks for the EIA for 2013, projections for 2020. We assumed that all current air quality policies would be fully implemented by 2020. We picked 2020 as a reference year. And these other assumptions are invoked: wind power, production tax credit, as well as relicensing for nuclear units. And the results are shown here. Carbon dioxide emissions decreases by about 15% from 2005 values to the study year 2020. Okay, so then we looked at three scenarios, and these three scenarios are very diverse scenarios, and that was what we were trying to accomplish. First scenario, which was supported by the electric utility industry, we call the power plant improvements. It's a very modest proposal, low stringency, low flexibility. It's just really looking at heat rate upgrades, improving the efficiency of the individual plants inside the fence line. Very modest projections. Decreases in carbon dioxide, only 17% from 2005 values, only about a 2% decrease from the reference case. The third scenario, as it turned out, and we didn't really know what was happening, but it turned out this scenario is very similar to the actual Clean Power Plan. So we were extremely fortunate to come up with ideas that were similar to what the EPA came up with. So this is a moderate stringency, high flexibility plan. There are benchmarks that are established for each state. It allows states many compliance options. There's incentives for energy efficiency. It allows for averaging and trading. And so this plan, the carbon dioxide decreases are projected to be 35% from 2005 values, and this is a 23% decrease from the reference case. The final scenario is probably not very realistic, but I think it is a useful comparison, and this is a high stringency, moderate flexibility. It puts a cost on carbon at the social cost of carbon, which is $43 per metric ton. It doesn't allow for demand-side energy efficiency, so it's a very stringent program. As I indicate here, almost 50% decreases in carbon dioxide emissions from 2005, and about a 40% decrease from the reference case. So just a little bit about the baselines. I think baselines are very challenging. They're going to be very challenging going forward at evaluating the actual clean power plan because the energy dynamics is really extreme right now. And in fact, I'll show you some numbers from the EPA's projections from their draft case to the final case, and you can see they made major changes in the reference case. Okay, so these are some diagrams to show you the differences across these different scenarios. So this looks at the distribution of energy. The upper panel is from fossil fuel, and the lower panel here is from renewables and efficiency. So I've got these bars color-coded according to the scenario. So the blue is the reference case. The red is the inside the fence line, the power sector improvement, or power plant improvement scenario, the industry's option. The green represents the scenario that's similar to the Clean Power Plan, and the purple represents the plan that's a simulated carbon tax. So I won't sort of belabor these, but just point out a couple of interesting aspects of it. If you look at the power plant, the inside the fence line plan in red, you can see there's actually a slight increase in sulfur dioxide emissions. Very small, but a slight increase over what was the reference case. If we look at the Clean Power Plan, you can see the big thing is through decreases in generation associated with improved energy efficiency, shown here. And then with the carbon tax, because of the higher cost of carbon, you can see these higher costing technologies come into play. So you can see there's an increase in carbon capture and storage. It couldn't be implemented in 2020, but it becomes economically viable. And then you can see there's more generation from these other technologies that are more expensive. So in terms of how this translates to projection emissions, these are shown here. And you can see that for the coal with the power sector scenario, with the improved heat rate, you can see that there's a slight increase in sulfur dioxide emissions here. And that's because if we improve the energy efficiency of these old units, they move up in the dispatch list and they burn more high sulfur coal. So it's not very large, but it's reflective of a phenomenon called emission rebound. The power sector improvement scenario doesn't really show major changes in emission reductions for these, or changes in emissions of these co-pollutants. The other two scenarios show, marked decreases projected for sulfur dioxide, nitrogen oxide, and mercury. Okay, so this is just a summary of what I just said. So for the weak standard scenario 1, very modest changes relative to the reference case, and the other two standards, the flexible standard and the energy tax scenario, you can see pretty large decreases in sulfur dioxide, nitrogen oxides, and mercury. Okay, so I mentioned that one of the things that we did was fortunate was to try to make spatially explicit output. So we produce maps like this map. And so what this is the difference between the scenario that's similar to the Clean Power Plan and the reference case in terms of projected changes in PM 2.5. So the more brown the color, the greater the decrease in PM 2.5. So this is on a 12 kilometer by 12 kilometer grid, and you can see that this is the decreases, if I can make my laser pointer, fairly prominent decreases throughout the eastern part of the country. This white circles represent areas where there are power plants, and so you can see that there are large parts of the country that have projected improvements in air quality through PM 2.5. And the browner the color, the greater the decrease. So this is a scenario which is the difference between the, for fine particles, the power plant improvement scenario, the weak scenario, scenario 1, relative to the reference case. And you can see there are very modest decreases. In some cases, there are some very limited deterioration in air quality associated with these increases in sulfur dioxide, but by and large, not much change. These are maps for summer ozone concentrations, again, between the scenario 2 and the reference scenario. You can see the benefits for ozone, again, with the darker brown colors, are more distributed around the country. So there are a number of states in the Mountain West that have substantial benefits. And then this is the same type of scenario for scenario 1 for ozone relative to the reference case. And again, you can see rather modest changes. Okay, so I mentioned that we took these air quality outputs, we put them in BenMap. These are the outputs that we looked at for fine particulate matter. These are the health outcomes that we looked at for fine particulate matter and ozone. I think we took a relatively conservative approach. We took relationships that we felt were very well vetted and were well established in the literature, so I think our estimates are probably fairly conservative. This is a state-by-state basis for the lives saved from the scenario that's similar to the Clean Power Plan. The deeper the purple color, the greater the numbers of lives saved. So this is just a reflection of what should be obvious to you. The states that have the greatest number of lives saved have two things going for them. They've got a lot of people and they've got poor air quality. So states like Pennsylvania, Texas are the ones that show the greatest benefits in terms of deaths avoided associated with elevated PM and ozone if you would implement a standard like the Clean Power Plan. I should point out that all 48 states have positive outcomes, so all 48 states have benefits, but the benefits are very heterogeneous, much greater benefits in the poor air quality eastern part of the U.S. This is the same slide, but it's a normalized on a per capita basis. So you can see really the distribution normalizing across population density. And so this is really a reflection of both the two slides I showed you for PM and ozone, reflecting both of those conditions. And we, as I mentioned, we did a number of health outcomes. These are, I'll show you another one. This is hospital admissions avoided, and again on a state-by-state basis for the scenario that's similar to the Clean Power Plan. The other thing I did, I mentioned that this was really, an outreach was a big part of this. So we produced infographics that we used in our outreach phase. This is the national scale infographic talking about the changes in emissions and the improvements in terms of ozone and PM, and then the health outcomes. So this is on a national basis, but we also produce state-specific infographics. So if we talk to a group from Missouri or Texas, we would have that specific information. We could report to individuals from specific cities. So if I got a call from somebody from Chicago or St. Louis, I could give them the specific information on what sort of benefits that they might experience in those specific cities. So I think that was one of the advantages to the approach that we used, because we had local scale air quality that we could have a direct dialogue with people on what the effects of that would be. EPA had a lumped approach, so they looked at a regional basis, but we were able to drill down and talk about the specific issues with specific local areas. We've also done a very limited cost benefit analysis. And so these are the numbers based on that. So from output from BenMap, the health co-benefits, we estimate the central estimate is $29 billion per year for the scenario 2, which is similar to the Clean Power Plan. This is the confidence interval. If you make a very crude estimate for what the carbon benefits would be associated with the social cost of carbon, you can see that they're of the same order of magnitude. And then we have an estimate of the annual costs at about $17 billion. And then we also looked at evaluation of how we estimate those costs and the assumptions associated with those costs. So we think there's very strong net benefits for that. So I mentioned a piece of this. Because of time, I'm not going to go into this in great detail, but this is actually what I do. I don't do anything in health benefits. I'm really an ecosystem guy. So as I said, we look at ozone effects on crops and production and acid rain effects and visibility effects. So I'll show you a few slides of this. So we made estimates of changes in visibility to try to look at the implications of this relative to the regional haze rule. Part of the advantage of this is to try to engage states in the West that maybe have less health benefits but are quite interested in visibility. So the slide on the upper panel is color-coded. The colors that are more reddish show the greater improvements in an absolute measure of visibility at these class 1 areas where visibility is monitoring, mostly national parks areas. And so you can see the absolute improvements in visibility are mostly in this area right here in the eastern US. That's expressed in a sort of an obscure unit called deciviews. But this panel right here is it's in units of years. These areas that are out of compliance with respect to the regional haze rule are on what's known as a glide path to move towards meeting visibility goals by the year 2064. So this gives you the number of years that would advance that area towards meeting their visibility goals. And so we see, because of the higher visibility in the West, you can see greater time towards their glide path in areas of the Mountain West. We also looked at effects on crops, ozone effects on crops and timber. So we looked across the spatial distribution of a number of crops and also a number of forest sites. And these are, I have to apologize, these are god-awful plots. They're terrible, but let me try to show you what they're showing. So these are for a particular crop. The gray bar represents the reductions, the integrated reductions in production that is estimated for this crop given the spatial distribution. So you can see that this is a productivity reduction scenario. So the axis for the gray bars is shown right here. And then if you've got good eyes, you can see these 3 colors in here. They represent the 3 scenarios, and that's the scale on the other side. So that is the percent of alleviation of that productivity or improving that productivity loss associated with reducing the ozone concentrations. So for example, for soybeans, the scenario that's similar to the Clean Power Plan would alleviate loss of soybean production by about 7%. So we did this for a number of crops, and we did this for a number of trees to try to assess the potential impacts on crop and timber production. Okay, a couple more things before I close. One thing we were interested in was looking across this policy space. So this is sort of an integrating figure. This panel is sulfur dioxide emissions, nitrogen oxide emissions, and this is premature deaths avoided. And these color codings, the triangles, the purple, blue, dark blue, and light blue, represent the 3 scenarios that I just presented to you. And these are relative to carbon dioxide emissions avoided. Okay, so this is sort of looking at the stoichiometry, if you will, of how sulfur dioxide changes and nitrogen oxide changes and also deaths. And then here in the circles represents the draft Clean Power Plan, which was 2014 in the dark green, and the final plan right here. So you can see there's pretty large changes here And that's reflecting this shifting baseline that I talked about, the fact that the assumptions concerning renewables and natural gas change between the draft plan and the final plan. And you can see our scenario 2 falls approximately within that space. But the three scenarios have very different outcomes. Okay, so the other thing that I mentioned is that we are looking at the actual Clean Power Plan, and so we're trying to address the question, what are the implications of different ways in which this might be implemented, and would there be associated air and health and ecosystem benefits with that? So as I mentioned, this is going to be implemented in theory in 2030. And there are a number of trade-offs that are being considered. One is the way states would assess this. Would this be a mass-based approach where there would be a cap for a particular state, or would it be a rate-based approach where there would be emissions per unit? And what are the implications of that? Does it include existing units only, or new and existing units? Is there trading options that are available that would be implemented? And so we're trying to do a similar approach, but look across these different options and evaluate what the implications would be. So we'll use a very similar approach right now. We've only done the first part, the emission piece. So this shows you the emissions, the carbon dioxide, sulfur dioxide, and nitrogen oxide for these various scenarios, looking at the mass base, rate base, trading, no trading, and so on and so forth. And at first blush, there's not very much difference on a national basis. But if we look across these states, the implications for, this is carbon dioxide, but particularly sulfur dioxide, these different scenarios play out differently across the states. And so we'll use a similar approach to look at the air quality and look at the health benefits and how they're spatially distributed. But that's all in progress now. So just to close this up, so the project that we finished up, we found, and these are sort of no-brainers, that a program to control carbon dioxide emissions from power plants that's stringent and flexible, that's like the Clean Power Plan, has widespread benefits. I mentioned that all 48 states have some health and ecosystem benefits. The top states for premature death avoidance are shown here. So things like I told you, Pennsylvania, Ohio, and Texas, with poor air quality and high populations. And then our cost-benefit analysis say that the benefits far outweigh the costs. So this is what I told you before, that shifting to cleaner energy sources, greater energy efficiency, better air quality, good health and ecosystem co-benefits. And I think our experience was that resonated with a lot of people, and people were interested in that. And so I think it's a good approach to talk about the advantages of the Clean Power Plan, to try to give people that they can relate to. I also think that there's a lot of co-benefits out there, and I think it's a good approach to dealing with these problems, particularly problems that don't resonate well with people, to put it in terms of things that they can understand and try to turn the conversation in that direction. So if there are any questions, I'm happy to try to answer questions. Yes?
I'm Sam from Palestine and visiting scholar at MIT. I'm just curious to know whether you consider the climatic change implications on the policy, where we can see some signs of a colder winter and a hotter summer, which will reflect on increasing the demand of energy.
Yes, you're right. We did not look at that. We did not look at the climate implications. We really had a very focused project just looking at the air quality benefits, both on the ecosystem side and the human health side. But you're 100% right. There are going to be effects in terms of climate on these co-pollutants, and in many cases the situations will be exacerbated because of warmer conditions. So that's a very important dimension of that. We did not do that. Yes?
Hi, Mike Sanford. I'm from the Mechanical Engineering Department and Solar School. Is there a movement to do this in other countries where the mix of coal is probably even makes up a larger percentage of the energy mix? Take for example China, where air quality is even worse, where they would see probably even bigger benefits from a study like this in the United States.
Yeah, so I think that that's a very likely situation and needs to be done in the worst way. I mean, we have some benefits, but they're relatively modest benefits. I mean, we've had tremendous improvements in air quality in the last 20 years, but I think if you did a similar analysis for one of these other countries that are really challenged in terms of air quality, you would see massive co-benefits, which could, hopefully turn the conversation towards the advantages of implementing programs like this. So we're hoping this type of analysis is a model for other countries, but also other sectors as well. I think there are other co-benefits dealing with agriculture and transportation. So I think it's a useful approach.
My question is on what the sensitivity of the climate reduced model. Do you have a reduced model for the climate, for instance, to go from ozone to smog? And is that what kind of data do you need to make this model more accurate?
So what we did was we used a reference meteorological year that is very similar to climate conditions that we've experienced, even though there's been a lot of variability in the weather over the last few years, something that's thought to be relatively, typical of the last decade. But we did not look at different climate scenarios and how that would influence the air quality model. That was well beyond the scope of what we could do. But that's a logical thing to look into for sure.
Because let's say if you're looking at 20 years, in the first 7 years you have heating, right? That changes, let's say, the occurrence of El Nino, and then you have nonlinear feedback.
Yeah.
So that's going to either exacerbate your outputs.
Yeah, no, you're 100% right. Yeah. Yes?
The energy landscape has changed since you started this project. If you were to do it again now, like in the beginning, is there anything you would add or take away, or?
Yeah, so I think, as I said, I think there's some things that we did well. I think we took money from foundations. So I was talking to some of the students and postdocs, you among them. And one of the outcomes of this that we got to the attention of the Heartland Institute. They got very animated about this study, and they said that we misrepresented the funding source. They said we had funding from EPA, which we didn't. We had funding from the Hewlett Foundation, the Grantham Foundation. So I think not having EPA money was beneficial to us in that regard, and so I think that that was useful. I think doing this spatially explicit approach, that was very advantageous for us. I think it would allow us to have those local scale conversations, which we found were very useful, and I think increase the impact. I think the reference case is a huge problem, and I think we need to do a sensitivity analysis on that. As moving forward, when we're having this dialogue about the current project, we're talking with a lot of groups who have very strong opinions about what they want to see for outcomes, and the reference case has a huge implication on that. So if you think about how much energy use has changed over the last couple of years and think we're extrapolating over to 2030, I mean, you probably know better than I. It's a very daunting undertaking. So I think having some sensitivity to that, and I think the reference case, all the benefits are really wrapped up into the assumptions that you make with a reference case. So I think going forward, I think we have to try to do a better job characterizing this. But because we have this sort of linked project where we have different groups doing different pieces, it gets very expensive to do that. And so that just drives up more scenarios and increases the cost of the project, which makes more challenges for fundraising. But I think it's really critically important. So I think that things worked out relatively well for us. I think we had a good dialogue, a healthy dialogue with EPA. I think they were generally happy with what we came up with. It was sort of an independent analysis, but there was also some tension there as well, which I think is good, and I think that's useful. And I think, you know, we had a lot of discussions with a lot of groups. I talked to a lot of states that are not very, people from states who are not very enthusiastic about the Clean Power Plan, but they're very worried about their local air quality. So I think I think it was a useful exercise. Yes.
So we've seen here in the results you showed some of the co-benefits. I was wondering if through this study, or even perhaps if you take a look at other dimensions to this, are there any disbenefits or trade-offs that can be made? One example I saw was the slight increase in SO2 emissions as a shift towards more coal power plants. Do you see that as being large in magnitude? Maybe if you look at other cases, or do you see that as non-existent?
No, I think there are dimensions, and I think even though we were on sort of a limited budget, limited scope, I think the fact that we did use these very contrasting policy spaces, I think it was very useful. I think we tried to do a scenario that was really strongly supported by the energy industry, and it showed very limited benefits, and it showed this emission rebound problem. I don't know within the context of the Clean Air Act whether that could actually happen or not. I've talked to people. Some people say maybe, some people say no. But I think that was an issue. I think also, if you think about this, the carbon tax was more effective. I mean, taxes are sort of non-starters, but I think it did show that you could have a system that was high stringency, but it wouldn't produce those co-benefits. So there are advantages to promoting, you know, sort of no-brainer and renewables and energy efficiency. But I think it was, you know, the analysis sort of pointed out the advantages of that, and I think it was useful in that respect. Yes, sir.
You mentioned that every state saw some benefits and that in net the benefits exceeded the cost. Did you look at the distribution of the net cost benefit?
Yes, we did, and we did it by ISO regions. And I was going to put on a slide. I was a little worried about the time, but certainly the immediate benefits exceeding the costs were the case for 10 of those ISO regions, but depending on your assumptions that, you know, those health benefits, I mean, we only did them for 1 year, but they're going to continue over many years. And so eventually, given enough time, I think up to maybe within 5 years, I think it's 13 of the 14 ISO regions would move to positive net benefits. Certainly the states in the Pacific Northwest receive the least benefits. So it's mostly in the areas where air quality is most challenged, where there were the most immediate improvement, cost benefit metrics. Yes.
I have to give a former grad more credit for this question, but is there a possibility to extend these results on the health benefit side to socioeconomic or racial divisions?
Yes, that's a great question. We've been under a lot of pressure to do that, to try to look at environmental justice issues, and we will likely do that for the current project. We just didn't have the time and resources to do it for this project, but there's a lot of interest in looking specifically what are the local areas and they're receiving those benefits, and so that's something that we have our eye on and may do in the future, and there's a lot of groups that are particularly interested in that question.
One of the slides showed the social cost of carbon as $1.40 or so. So how did you guys come up with that?
I didn't come up with it. It was an EPA. It's an EPA value. I think that's the median value. Or when we did the analysis, yeah. Yes, sir.
This is a hypothetical question in a way, but maybe your group or maybe you know. Suppose we shut off all carbon dioxide production tomorrow. What would happen to climate change due to existing carbon dioxide?
Well, it would change, right? I mean, but carbon dioxide has a relatively long atmospheric residence time, right?
Due to its effect on climate change.
its immediate effect on climate change?
Or long range, if we shut it off tomorrow, what's the trend after that?
So do you mean anthropogenic carbon dioxide or all carbon dioxide?
All carbon dioxide.
We need carbon dioxide, right? If we didn't have carbon dioxide, we'd be in deep doo-doo. We're all carbon-based systems, right?
A hypothetical question, I just want to have that limiting case compared to all the other cases we hear.
Okay, well, I'm not exactly sure where you're coming from, but if we got rid of carbon dioxide,
Coming from anywhere, just limiting case is a thing we often do in our studies here.
I would think plants would die immediately and we would die as soon as our food stocks, it would have catastrophic effects, if I'm understanding your question properly.
Maybe the plants would not die. They've got carbon dioxide to get out of the atmosphere.
Okay, maybe I'm not understanding your question. I thought that you were going to cut it off, so I thought that maybe it wasn't available to them.
Basically, it comes down to if we just maintain the current CO2 level without increasing it.
Oh, I see. Okay. Well, then I think things would start to reverse, and we would start to come into steady state with respect to the current value. But it would take a long time to play out. It would take
Is it higher or lower? The new steady state you talked about.
Well, it's a very complicated question because we're never really at steady state, but it would approximate steady state, I would think, given our current conditions of weathering and, the carbon dioxide concentration has been driving down in the Earth's system for years and years and years, hundreds of thousands, millions of years, and it's starting to reverse back. So it would start to probably go back to its original trajectory, would be my guess.
That's a good point to thank Charlie again and say that we can have some more informal conversations on the climate system and air quality out at a reception. So let's thank Charlie again.
Thank you.